Thank you, Bernard, for inviting me. So I didn't quite know what to expect. So we'll see how this goes. Yeah. So and I discussed with Yasha. We were also not uncertain what might be most interesting for you. So we settled on something which is related to the boundary between complex and symplectic geometry. And I will give an introduction on the corresponding objects, notions of convexity that appear there, and then lead to Stein and Weinstein manifolds and end up hopefully indicating why those are equivalent notions. And then Yasha will talk about something more specific in contact geometry, as I understand. Yeah? Okay, so, and feel free to interrupt me and ask questions anytime. So I want to start with notions of J convexity, where J will be, for me, a complex structure. I start a bit more generally first. So let me make this slider. So we start with maybe an almost complex manifold. So J is an almost complex structure. And let's always say that the complex dimension of this manifold is little n. And then if we're giving a function on that manifold, smooth function, then we can associate to it a two form, which I will denote by omega sub phi. We take minus d dc phi, where dc phi means we take the differential of phi, which is a one form, and we compose it with the complex multiplication. So we get another one form, which has no longer any reason to be closed. So we take another d of it, we get a two form. Yeah, so this is an exact two form. And then in this notation, we can say that a function phi is J convex if this two form is positive on complex lines, meaning omega phi, if I plug in some tangent vector and J times this tangent vector, this should always be positive for all non-zero tangent vectors. Okay, so this is the same as saying this is on the tangent space, the condition. I could also say it as follows. If I take any complex curve C, local complex curve through any point, and I restrict my function phi to this complex curve, then this is also J convex. Yeah, so J convexity really is just a condition of what the function phi does when you restrict them to one-dimensional, complex one-dimensional curves. Okay. So what does it mean in explicit terms, and how does it relate to classical notion of convexity in complex analysis? So let's look at the basic example, which is C to the n with standard complex multiplication. And then you can work out that this omega phi, you can write it as 2i times del bar phi. So partial derivatives with respect to complex coordinates zj and zj bar. Yeah, and then for n equals 1, you can just work out in coordinates what it means, and you get a multiple of the Laplace operator in complex dimension 1. So phi is I convex with respect to this complex structure I, the standard complex structure, in complex dimension 1, if and only if Laplace of phi is positive, meaning that the function phi is subharmonic. Yeah, and then by what I said before, if you go to higher dimensions, then this function phi is I convex if and only if its restriction to every complex line is subharmonic, and such a function is then called plurisubharmonic. Yeah. So phi subharmonic on each complex line. Okay, so this is just to fix some notation, and now there's, from this description of what it means to be I convex or J convex, we deduce immediately. Let me just, I think I need to push Yasha slightly away here. Sorry, Yasha. Okay, now. Just 1 second. Here it is. Okay. All right. Okay. So the following lemma plays an important role in everything that follows. That if P is a non-degenerate critical point of a J-convex function, phi, then the index of P with respect to that function is less or equal to n. So this means so V is a manifold of real dimension 2n, but if on V you have a function, if that function is J convex, then the indices of its critical points can only go up to half the real dimension, only between 0 and n. And so you cannot have anything beyond half dimension. Okay, so this follows immediately, because if you restrict to any complex direction, then it's subharmonic, so it cannot have a local maximum. So in that direction, the index can only be at most 1, can only be 0 and 1 in every complex direction. Then you sum up and you see, because you have n complex directions, the index can be at most n. Yeah? So it's a very easy local lemma. So this was about convexity, J convexity in complex geometry of a function. And then we also need a notion which is closely related of J convexity of a hypersurface. So let's take sigma in V. V is still our almost complex manifold. Let this be a codimension, so of real codimension 1 hypersurface. Yeah, so it's a submanifold of real codimension 1. It's not a complex submanifold. And let's say we co-orient it by some transverse vector field such that J times V is tangent to sigma. So here's a picture. So we have sigma. It's of real codimension 1 in the ambient space, and then we take some normal vector field so that J times this one is tangent to sigma. Then we let C be the tangent space to sigma. So that is, of course, not invariant under complex multiplication. So we intersect it with its image under J. And that is now a codimension 1 distribution on sigma. So in the picture, I would draw this Xi. So this Xi is somewhere here then. Yeah. So Phi at every point P, you have a maximal complex subspace of the tangent space of sigma, which is a real codimension 1 in sigma. So it's a real codimension 1 distribution over sigma. And now we can define omega sigma to be d alpha. So where alpha, we write Xi locally as kernel of a one form. It's a codimension 1 distribution. So we can write it locally as kernel of a one form on M. And then we take d alpha and restrict it to this distribution Xi. So that gives a two form on Xi, and that's called the Levy form. And now we can say what it means for sigma to be J convex. Means that this Levy form is positive on complex lines. Yeah, so it's quite analogous. Let me maybe emphasize that in this generality, this Levy form is only defined up to multiplication by a positive function, because I wrote this distribution Xi locally as kernel of a one form, but of course I can multiply this one form by a positive function that still has the same kernel. Yes, so this is defined modulo multiplication by a positive function. So when we talk about properties of this Levy form, but you see this positivity is independent of rescaling by a positive function. So being positive is a well-defined notion. Yeah, and that's what we mean when we say it's J convex. And now, somehow expected relation between convexity of functions and of hypersurfaces, as you would hope. Namely, if the function phi from V to R is J convex, and let's say we restrict to a region away from the critical points. So that whenever we take a level set, it's automatically a regular level set, so it's a submanifold. And then it follows that its level sets, all level sets of phi, which are now codimension 1 hypersurfaces, are J convex. Yeah. This implication follows immediately from the definitions, and the converse is also almost true. It's true under some technical assumption if the level sets are compact. And you see, when we have a function where all the level sets are J convex, we cannot really expect this function to be J convex because the level sets do not capture what's happening with the function in the direction transverse to the level sets. That's not captured by the level sets. But this can always be remedied by composing this function with a sufficiently convex function. So after replacing phi by f composed phi for some convex function f from R to R. Yeah. So you can, if you don't have any intuition about J convexity, you can actually think about all those notions in terms of geometric convexity. So just think of Rn with a standard metric, and then we know what it means for a hypersurface to bound a convex set. So that is somehow a notion of convexity for hypersurface. And we also know what it means for a function to be convex. And if you have a convex function, its level sets are convex. But conversely, if you have a function where the level sets are convex, the function may not be, but you can make it convex by composing it, by post-composing it with the convex function. Yeah. So all this has complete analogs in geometric convexity in the real world instead of the complex world. Okay, so let's again see what this means when we go to Cn. So let's take Cn again as the ambient manifold. As complex structure, we take complex multiplication I. Let's also fix the standard symplectic form on Cn viewed as R2n and the corresponding standard Riemannian metric on C to the n. And now let's take in C to the n some codimension 1 real hypersurface. And then in this case, one can actually normalize the Levy form in a particular way by choosing a unit normal vector field and the standard symplectic form. Let me not go into that. There's a way to get rid of this ambiguity here we can fix it. And then suitably normalized the Levy form at a vector v and then I times this vector. We know it has to be positive if it's J convex. And this can be worked out. And this is precisely given in terms of the second fundamental form of sigma. You see, sigma is now a hypersurface in R2n with a standard flat metric. So it has a second fundamental form applied to V, plus the second fundamental form to sigma applied to I times V, rotated by complex multiplication for all V in this complex distribution, yeah, where this is the second fundamental form. So sigma is I convex in Cn if and only if the mean curvature is positive on each complex line inside the tangent space to sigma at a point. So you take a point on sigma, you take any complex line in sigma, so one-dimensional complex line which is contained in the tangent space to sigma, and then you take the mean curvature over that complex line. So you take a vector in that complex line and I times the vector and sum up the mean curvatures, maybe divide by 2. And if that is positive, that precisely captures this hypersurface being I convex. Okay? So this was for me, this was the main reason why I wanted to start with this one, because this is at least one place where some notion of positive curvature comes up in complex and symplectic geometry and in some work that we've done over the recent years. So this was the first part. Maybe there's some questions. Yeah.
Kai, can I interrupt for a moment?
Yes.
So can you remind us which normal vector field you're using?
Yes. Okay. Okay. So here we can normalize it such as follows. We take nu perpendicular to sigma. So really just the orthogonal vector field, and we normalize it to length 1. We have a metric. And now I need to say what is the one form alpha which defines this distribution psi. And as alpha, we plug that normal vector field into the standard symplectic form. And you can work out that then the kernel of alpha is precisely this maximal complex subspace. And that now singles out a specific definition of this alpha. And once I have this alpha, yeah, the Levy form is given in terms of d alpha restricted to Xi. Then everything is completely fixed. Yeah.
So, but the sign of the mean curvature depends on the choice of.
Oh, it should be co-oriented.
I see. Okay. Yes.
Okay. Just 1 second. Did I forget to say that, no, okay, I said it here. I still mean it to be co-oriented, and I pick, yes, so I pick the normal vector field, mu, in the direction of the given co-orientation. And of course, being I convex or J convex depends on the co-orientation. So when you change the co-orientation, then it's no longer convex, it's becoming concave. Yeah, so convex is depending on the co-orientation. Yeah, does that answer your question?
Yes, thank you.
So any other questions at this point? Or okay, then so this was the first topic that I wanted to mention, which might lead to some discussion and maybe some relation of things you're interested. And then the second one is I want to explain a little bit about Stein manifolds. Okay, so a complex manifold. Now we take an integrable complex manifold. So I will still write it as a pair V, J. J is the almost complex structure, but I assume it's Steenhaus tensor vanishes, so it's integrable. You know? So it's really a complex manifold. This is called, is a Stein manifold. By definition, and now I can use our previous terminology, if there exists an exhausting J convex function phi on that manifold to R, whereby exhausting, I mean that this function is proper, primitive compact sets are compact, and bounded from below. Okay. And then there's an amazing theorem where the most difficult part is due to Grauert, that this is equivalent to this complex manifold to admit a proper holomorphic embedding into some Cn of sufficiently large dimension. So as opposed to the case of real manifolds, which always embed into some sufficiently big Rn, it's not true for complex manifolds. For example, the compact complex manifold can never embed into Cn because of the maximum principle. Yeah. So and those which do embed into Cn in a proper way, so that when you go to infinity in the manifold, you also go to infinity in Cn. Those are precisely the Stein manifolds. And the amazing, so this is Grauert. The amazing thing is that you can characterize this fact of admitting a proper embedding into Cn just purely on the manifold itself in terms of existence of such a J-convex function. Yeah. So maybe just so we have something concrete, example is you take Cn itself and phi of z is a sum zi square. That's a good I-convex function, and it's bounded from below by 0. It's going to infinity at infinity, so it's proper bounded from below. It's an exhausting function, and it's I-convex. You just check it. Yes. So Cn is a Stein manifold. Cn itself, well, it's also clear because it embeds into Cn, yeah. But I mean, also from this other perspective, it's a Stein manifold, and it follows directly that any properly embedded complex submanifold of it will also be Stein manifolds. Yeah? So you take some polynomial equations, and they define you, if you're lucky, some Stein manifolds in Cn. Okay. Now, I had this lemma that the indices of critical points of a plural subharmonic function can only be up to half dimension. So from this lemma, we get the corollary that each Stein manifold is obtained from the ball, the 2n dimensional ball in Cn, by attaching handles of index at most n. Yeah, so you start with the ball, and then you attach handles to the ball of index being dimension of the core of the handle being at most n. Yes, or you could also say it more topologically that every Stein manifold has a homotopy type of a CW complex with cells only up to dimension n.
Kai,
Yes.
would like to ask something, namely, in your proper holomorphic embedding, the last n, can this be estimated?
Oh.
So what?
Oh yes, it can be, and we have the right person here, because I think the optimal estimate on how small you can choose n was established by Yasha with somebody. Yasha, can you remind me? Anyway, it's roughly little n times 3 over 2.
It's a Misha and Yasha.
Oh wow. Okay. Apologies. So we have both of them. Yes. So then any of you. I think the capital N is roughly 3 over 2 little n. Is that correct?
So it's a three half dimension.
Yeah.
No, don't ask me anymore. No?
Yeah. Yes. So. Okay.
Okay, thank you.
All right. And now, once you have this corollary, which is easy, it just follows from this local lemma on Morse indices, you can ask, is there a converse? So suppose I start with a real manifold of dimension 2n. When does it admit the structure of a Stein manifold? And then clearly a necessary condition is that it must have the homotopy type of a CW complex of at most half dimension. And question is that sufficient? And amazingly, it turns out that it is. And that is the first actual theorem I wanted to mention. So due to Yasha, that you take any almost complex manifold. So just given an almost complex structure of dimension at least of dimension bigger than 2, complex dimension bigger than 2, and phi from V to R an exhausting Morse function with such that index of all critical points is less than n. So those two conditions are clearly necessary conditions for it to admit the structure of a Stein manifold. So we need to have an exhausting, if it's a Stein manifold, it has an exhausting plural subharmonic J-convex function. If you perturb it to make it Morse, and then all its indices are less than n, right? So we need to have at least such a Morse function. And of course, if it's a Stein manifold, it's a complex manifold. So at the very least, it must admit an almost complex structure. And those two conditions are actually sufficient. So then this almost complex structure is homotopic through almost complex structures to an integrable complex structure. Let's call it J tilde such that the manifold with this new complex structure is a Stein manifold. And one can even explicitly say what is a J-convex function on that Stein manifold. You can almost take the original one up to maybe post-composing with a sufficiently convex function. So you can basically make your given Morse function a J-convex function for an integrable complex structure, which makes this whole thing Stein. Yeah, and I mean, if you ever spend any time on complex geometry of compact manifolds, then I mean, this is of course completely a different world, because in general there's absolutely no means to construct a complex structure on a given compact manifold. But surprisingly, here in this setting, you can actually, out of almost nothing, you can construct an integrable complex structure. Yeah. Okay, so let me, maybe because of time, I was planning to say a couple of words about the proof, but let me skip that. I mean, if we have time later, I'd be happy to give a few comments. But it turns out that really the main part of the heart of the proof is explicit constructions of J-convex functions. So you construct this Stein structure by starting with the Stein structure on the ball, and then you extend it over handles, because we know we can represent our manifold by handle attaching. So we need to extend it over each handle, and then you first need to extend the complex structure. That turns out to be not so hard. And then the harder part is that you also need to extend your J-convex function that you had before over the next handle. And that really requires some quite subtle local constructions of J-convex functions, which, yeah, there's a lot more to be said, but let me maybe just leave it at that. So then the last topic I want to touch upon, unless there's any questions at this point.
Okay. So why is this holomorphic embedding into CN large and useful? What are you doing with it?
To understand things about the complex geometry of these manifolds, I don't know. I think it's...
Yeah, but for instance, you see how many holomorphic functions, like people in complex wants to study holomorphic function on the manifold, and then restriction of, like on CN, we have quite a lot of functions, and we can...
That is true, yes. Mm-hmm.
Yeah, that is true. Yes. For instance, I mean, I skipped many other definitions, actually more classical, of Stein manifolds. And one of the other definitions involves, for instance, the fact that holomorphic functions should separate points on the manifold. So there need to be enough holomorphic functions that for any 2 points you find holomorphic functions which take different values at those 2 points. And that's something which of course you immediately see when it embeds into CN. And but when you start with the more intrinsic definition, just having a J-convex function, then it's really a deep problem to construct holomorphic functions on that. It's completely unclear where they would even come from. Yeah. So that is maybe, yeah, I think that's the answer. Mm-hmm.
This last theorem that you mentioned here of Yasha's, is this an H-pole type theorem?
Yeah, I would say it is, and I think yeah, I'll say more about this. I think this is a starting point of a development more in the direction of which looks more and more like H-principle type statements. But of course, you can say this is already a zero parametric H principle. Yes, but what I'm going to say, if I have a little bit of time, is that there's actually also one parametric versions and so on of such H principle statements. Yes, so you should use it as an H principle type statement. Yeah, I think so.
So for instance, for this your positive scalar curvature, this theorem of Gromov-Lawson as of construction of this positive scalar curvature is of course H principle, and this is exactly in the same spirit.
Okay, that's very interesting.
Yeah. Yeah, I think I may actually say a bit more about this H-principle aspect now in this third part. If I think I have some 10 more minutes or so. Yeah, okay. Mm-hmm. So this actually let me get to this right away. I'll change the order a little bit. So let me talk about flexibility versus rigidity. So this is precisely about the question: to what extent does an H principle hold or does not hold for Stein structures? And I want to mention two fundamental theorems in this context. So, well, no, I mean, the first one, two more. The first one was Yasha's existence result, which you could see as a zero parametric H principle. So when some topological conditions are met, then a Stein structure exists. And now we can ask the one parametric question. Given on the same manifold two different Stein structures, are they equivalent in a suitable sense? And I will say in what sense. Yeah, so sorry, this is not. So this is a theorem by Mark McLean on on Cn. There exist infinitely many Stein structures that are formally homotopic What do I mean by, okay, first of all, I'm writing Cn, but you should think of it as just a real manifold. Yes? I think maybe it would be better to write R2n here. Yeah, so not with the complex structure. And I should also say that n must be bigger than 2. Yeah. Okay. So R2n for n bigger than 2, there exists infinitely many Stein structures. So a Stein structure comes with its own complex structure and an exhausting fluid subharmonic function on R2n, which are formally homotopic. That just means that the almost complex structures are homotopic as almost complex structures. So it's,
but of course on R2n it's not
on R2n it's automatic because there's no topology. Yeah, but I'm just writing it that way so because I will say something how it even generalizes further in a moment. Yeah, so that are formally homotopic, but that are pairwise not Stein homotopic. Where Stein homotopic means that they're homotopic through Stein structures. Now you have to be a little bit careful because the manifold is not compact, that you need to carefully define what a homotopy of Stein structures means. So you want to prevent critical points from running away to infinity, basically during that homotopy. So but one can phrase the notion of what is the correct notion of a homotopy of Stein structures on R2n, and then this is precisely a failure of the one parametric H principle. Yeah. So you have two different Stein structures. You ask, they can be connected through formal solutions, but they cannot be connected through actual solutions, through actual Stein structures. Okay. And it fails in a drastic way. So there's infinitely many on Cn or on R2n. And in fact, if you combine it with some more recent results, actually the same effect, that there's infinitely many different Stein structures, holds on any manifold that admits a Stein structure at all. So you take any manifold as in Yasha's theorem, which satisfies the topological requirement of admitting a Stein structure, and then there's automatically infinitely many which are pairwise not Stein homotopic. Okay, so it fails really in the maximal possible way. But then on the, well, I don't know whether it's upside or downside. Maybe some people like H principles to fail, others like them to hold. Yeah, so it depends on your taste or maybe the time of the day. And there's the last theorem that I want to mention is due to M.E. Murphy.
And maybe here you just say also, but in n equal to 2, it is unique, in fact.
Yes, in n equal to 2 on R4, Stein structure is actually unique. Yeah.
Which is kind of, in main part is due to Gromov, but like in some addition of Kai and myself.
Yes. Yeah, thanks, Yasha. Yeah, thanks for pointing that out. Indeed. Yeah. So this assumption n bigger than 2 is essential, both in MacLean's theorem, and I also had the same assumption in Yasha's theorem, n bigger than 2, and also Yasha's theorem fails for n equals to 2. Yeah, so there is 4 manifolds which satisfy like S2 times R2 or something like that. So that satisfy the formal requirement, but they do not admit a Stein structure. Yeah.
In MacLean's theorem, which invariant distinguishes Stein from copy class?
This is a great question, and let me actually add it here before I'm stating Murphy's theorem. So this is using something which I will not have time to talk about, namely, actually, yeah, okay. Let me just add it down here properly. So there is some symplectic notion underlying a Stein structure. So let me say a little bit how this is proved. So if you have a Stein structure, it's a complex structure with an exhaustive plural subharmonic function. You can associate to it something which is purely symplectic, and we already had this 2 form omega phi, and when phi is J convex, then omega phi is actually a symplectic form. Then you have the function phi, you keep it as part of the structure, and you define a vector field. You take the gradient of this function with respect to a metric g phi, where the metric g phi is defined in terms of the data by taking this 2 form omega phi, and you insert the complex multiplication in the second component. Now, J convexity precisely says that this g phi is a Riemannian metric. Then you take the gradient with respect to that metric. Okay, so this is now this is something that we call a Weinstein structure. So abstractly, Weinstein structure is a triple consisting of a symplectic form together with a function and with a vector field satisfying certain requirements. Okay, so this is a purely symplectic notion, and note that we've forgotten some of the most rigid part of the structure, namely the integrable complex structure. We've thrown it away, and we replaced it by something which is purely symplectic. And if you heard anything about symplectic geometry is much more flexible than complex geometry in a way. Yeah? So anyway, what we need here is only this thing. So to associate it to every Stein manifold, we have canonically a symplectic manifold, but now we have plenty of invariants of symplectic manifolds. And these different Stein structures are actually distinguished by symplectic invariants. So they are distinguished by a symplectic invariant called symplectic homology. Of the underlying Weinstein structure. Yeah. So we forget the Stein structure, we just look at the Weinstein structure, and then for this structure we can define some symplectic homology theory, and then MacLean constructs these examples and computes symplectic homology for these examples and proves that the symplectic homologies are all different, so they distinguish them. So this is really a symplectic result, fundamentally. Okay, now let me conclude my talk by at least mentioning this one other theorem, because this is now an actual positive H principle type result. So this is the theorem that I had started on. The main part is due to Emmy Murphy. Then with additions also by Yasha and myself to it, that every manifold admitting a Stein structure i.e. as in Yasha's theorem, admits a so-called flexible Stein structure. So that's a Stein structure which has some particular properties, and these flexible Stein structures are unique up to Stein homotopy. Okay, so there is a definition of what it means for a Stein structure to be flexible, and then when you restrict to the class of flexible Stein structures, you have a one-parametric H principle. Namely, first of all, you have a zero-parametric one on every manifold meeting the topological conditions. There exists a flexible Stein structure, and if you have any two flexible Stein structures on the same manifold that are formally homotopic, then they're actually Stein homotopic. Yeah. So this is a positive H principle type result also in the one parametric case. And I have no idea, but it might be also that there could be higher parametric versions of this, but this is completely open. Yeah, but there seems to be.
So I think that's also important to say that it's all this also in dimension starting from 6.
Yes. Also again, n bigger than 2. Yes. So dimension 2n, n bigger than 2, starting from dimension 6. Again, everything falls in complex dimension 2. Yeah.
How's the flexible Stein structure related to the original one?
So the thing is that in the construction of the Stein structure, in the proof of Yasha's theorem, how to construct a Stein structure, you make certain choices, and you can make the choices such that the structure you construct becomes flexible.
Okay.
Or alternatively, you construct this Stein structure and don't care, just quote Yasha's theorem, and then there's actually a stabilization procedure that, given a Stein structure, well, not so easy. No, I'll take it back. So you construct it directly to make it flexible. Yeah, I mean, yeah.
But important to say that flexible is not so exotic. For instance, standard structure on CN is flexible.
Yes, right. So flexible is only, so remember that the Stein manifold is a handlebody with cells only up to dimension n. Now, and somehow the thing that could make it not flexible lives only in the cells of dimension n. So if you're only having cells of dimension less than n, which is the case, for example, on Cn, yeah, that only has a 0 cell. So if all the cells have dimension less than n, that's automatically flexible. And on the n-dimensional cells, there is some condition. They are attached along a Legendrian submanifold in the boundary of the previous domain. And Legendrian submanifolds of some contact manifolds do not satisfy an H principle in general. But there is a class of nice Legendrian submanifolds, which Emmy Murphy introduced, so-called loose Legendrian submanifolds, and they satisfy an H principle. So you need to make sure that you're attaching your n cells along Legendrian spheres which are loose in Emmy Murphy's sense. And then it's flexible. But as Yasha says, for example, if you don't have any n cells, then it's automatic. Yeah, so it's they are not so rare. Mm-hmm. Yeah. Mm-hmm. Yes. Okay. I think my time is up, so I would stop at this point and hand over to Yasha.